Welcome to numerical ship and offshore hydrodynamics. Today's topic is wave and wave effects. So, today we are going to discuss something about the free surface waves and other things, and this is the keyword that we are going to use to get this lecture. Now, let us coming back to this kinematic free surface boundary condition. Now, if you look at the wave, then actually this water waves and this the black line, you can see it is basically border line between the air and the water, and this surface we call the free surface. Then what is would be the equation for this free surface? Now, if you assume that the coordinate axis that vertically upward is the z, so we can assume this vertical distance z is basically a function eta, which is depending on x, y and t. Now, here in two dimensional case we cannot see the transverse axis, but one can see that if you travel along this x axis, this eta will change, right. Also, if you fix that x at some point, let us say we are fixing somewhere here the x, and if you try to vary your time, then you can see the same kind of sinusoidal wave. So, therefore, this eta is changes not only with respect to x, but also it will change with respect to t also, and of course, with respect to y also. Okay. Now, remember in my last class, when we called a surface to be a boundary surface, right, and the definition that we have learned in last class. Now, here I can simply write a boundary surface f, which is z minus eta x y t, right. Now, then this surface become f x y z equal to 0, or we can say it is f of r t equal to 0, right. So, till this point there should not be any problem, because in last class we discussed about that f would be a boundary surface etcetera etcetera, and here I can see this f we can call as a free surface, because it is the surface which is between air and the water. And also I have discussed in the last class, and this is the one of the key things or say unique thing for ship dynamics or offshore dynamics, that we have to deal with this free surface, right. Now, let us try to find out that what would be the condition that a water particle will stick on this surface, right. So, the objective is to find out a condition, so that a water particle should stick on this surface. So, assume that this a water particle over here or somewhere over here. So, then what is the condition that this water particle cannot come out of the surface. Now, what would be the condition for this? So, let us try to find out. Now, if you remember my last class, what I said that a water particle or a particle stick on a boundary if and only if the normal velocity of the surface should be equal to the normal velocity of the water particle, right. Okay. So, therefore, here and this would be the condition that material derivative should be equal to 0, right. So, f be the boundary surface, then the condition should be df dt equal to 0, right. Okay. So, this everything we discussed in the last class. Now, here let us in the right hand side, actually I just derived that df dt is how I can break it in partial derivative. So, this is the vector notation, df dt can be written as df dt plus q dot grad f equal to 0, right. And then this q actually has three component, that u, v and w, right, and grad is of course I del del x plus j del del y plus k del del, right. Okay. Now, we assume that material derivative z minus eta that should be is equal to 0. So, this is the condition. Now, here if you remember that in my last slide I said that d dt of f should be 0. Now, I substitute the f over here and we know that in here actually we write that f equal to z minus eta x t. So, I substitute this f over here, right, and then I substitute that d dt also. Now, d dt is nothing but from here I know that it is del del t plus q dot grad. Okay. So, now what I do is this del del t I replace over here and therefore, if I replace this q then I will get this grad if I replace over here then I get it is u del del x plus v del del y plus w del del z, right. So, it is very elementary. I just change that q dot grad, I just get q equal to u I plus j v plus w k and I call grad equal to del del x plus del del y plus del del z, and if I do the dot product it should be u del del x plus v del del y plus w del del z, right. Okay. Now, I just do the operation. Now, here this z is not function of t, however, this eta is function of t, right. So, therefore, del del t of eta I just write minus del eta del t. Now, again z is not the function of x either, but eta is the function of x. So, I substitute over here. So, I get minus u d eta del x. Similarly, z is not a function of y also, however, eta is a function of y. So, if I do this then I get minus v into d eta d. And finally, that del z this goes to 1. So, I have the w, but then eta is not the function of z. So, therefore, it is 0. So, if I do this operation, so I will get minus del eta del t minus u del eta del x minus b del eta del y plus w, that should be equal to 0, right. Now, so now I understand that this is the equation, but where I apply this, that means that at which z this will apply. Now, if I write it this again the graph, I can see that this equation apply on the free surface. So, that means at the free surface your z is equal to eta, right. So, therefore, we understand that this kinematic free surface boundary condition, it is w equal to del eta del t plus u del eta del x plus v del eta del y, and it should be applied at z equals to eta. So, now I replace the u equal to del phi del x, v equal to del phi del y and w equal to del phi del z in this equation, and then finally, I get the complete expression as del phi del z is equal to del eta del t plus del phi del x into del eta del x plus del phi del y into del eta del y, and this apply at z equal to eta. So, this is my kinematic free surface boundary condition, which states that water particle has to stick on the free surface. If it is so, then this condition should apply or this condition should hold. Now, I am just writing this or writing in a little bit compressed way or smart way. So, I just write instead of del phi del z I use phi z, instead of del eta del t I use eta t. So, in that way I can write phi z equal to eta t plus phi x eta x plus phi y eta y, and this apply at z equal to eta. So, this is known as the kinematic free surface boundary condition. Okay. Now, let us move on the next part is called the dynamic free surface boundary condition. Now, kinematic free surface condition explain you that at this the water particle kinematics, that means water particles to stick on the free surface, right. Now, this dynamic free surface condition is telling you that at free surface there is equilibrium of the pressure. So, that means the difference of the pressure I mean the air pressure and water pressure balanced each other and this goes to 0. Now, if we apply in the Bernoulli's equation or my pressure equation, so this is the equation that we learned, the pressure equal to del phi del T plus half grad phi square plus g eta, we have discussed in the last class. So, here we are not deriving it, right. So, this is one and then this left hand side should goes to 0 because this one balance each other and then finally, we will get the dynamic free surface condition as del phi del T plus half grad phi square plus g eta equal to 0 and of course, it apply at z equal to eta. So, it apply over the free surface. So, therefore, I have two boundary conditions. One is we call the kinematic free surface condition which tells about the kinematics of the water particle and second one is the dynamic free surface boundary condition which talks about the pressure over the free surface. Okay. So, what is the complex part of it? Now, this is the equation, the derivation of the equation is fine, but what is the complex part? The first one is this is your the nonlinear kinematic free surface boundary conditions, right. And then we have the nonlinear dynamic free surface condition. Now, here needless to say in this equation 1 and 2 both eta and phi are actually unknown to me, right. Now, then the problem is how can I obtain phi if I do not know the information about eta and how do I obtain that eta if I do not have the information about the phi. Now, how to solve this problem? So, because you see this is a very this is really a complex part because now we get an expression for eta. So, in order to find the eta we need phi, also I have phi, but I need to find out in order to get the phi I need eta. So, the best way is just eliminate either phi or eta, right. So, how to do this? That means, we have here the both phi and eta both are present in the equation. I need an equation where that either phi or eta is absent. Let us see that. Now, classical book by marine hydrodynamics by J. Newman, he said that the kinematic free surface condition 1 can be replaced by the statement that material derivative of the pressure is 0 over the free surface. So, actually you can say this is a mixed boundary condition. So, it means that the pressure is 0 on the a varying surface. So, when I consider the a varying surface, so definitely it is a kinematic part and then we are considering the pressure is a dynamic part. So, what is said is very interesting. It says that I take the pressure along this free surface and that pressure should be equal to 0. So, that means I am considering now what I am doing as per his statement, I mean this statement, I am considering a surface of pressure. I am considering a surface of pressure where in this particular surface at any point of time the pressure variation is equal to 0. So, this is very strong argument actually and with respect to this we can easily eliminate the eta, right. How? Let us see. Now, you see here what I said that what I said the meaning mathematically meaning is that I just considering a surface where the material derivative of pressure should be equal to 0. Now, if I say that then this is the equation for the d dt, the material derivative. We know that is del del t plus u del del x plus v del del y plus w del del z, right. And then this pressure is basically this one, our pressure, right. Now, let us continue and let us find out what we can get out of this. Now, here you can see that in this equation there is no existence of eta, right. So, now if I break it, so I just write in terms of here actually what I did is this term I makes into two component, right. Now, you can see here I replace u by del phi del x, v by del phi del y and w by del phi del z, right. And apart from that, what I do that I write another component is I del del x plus j del del y plus k del. Now, you see if you do this, that means that is how I just make this this u del del x plus v del del y plus w del z. I break it this way. Now, if you do this, then actually you can get now if you use a dot product, it become del phi del x into del del x plus del phi del y into del del y plus del phi del z into del del z. See, this is nothing but your this term, right. And then actually what I do is I just use this as a vector product. So, I split it out in two vector component. One component is I del phi del x plus j del phi del y plus k del phi del z and multiply by the another component I del del x plus j del del y plus k del del z. So, I did that. Then what is the benefit of doing all these things? Let us see. Now, if I do that, then you can see that I actually write this term as a grad phi and then I write this term as a grad, right. And again just in case of del phi del t I make at phi t. So, therefore, this is the I write in a vector form. So, I just changes this into vector, nothing, is just a notation, right. So, now if I apply the differentiation over there. So, if I use del del t into phi t, I will get phi t t, and then if I get del del t into half of grad phi square. So, I will get grad phi dot grad of phi t, and also if I make grad phi dot grad of phi t, again I am getting grad phi dot grad of phi t. So, therefore, I get 2 grad phi dot grad of phi t, and finally, I multiply this with this. So, I will get g into grad phi dot grad into z. Okay. So, now I get a combined free surface boundary condition, which is the absence of eta, right. So, in this equation you can see there is no eta is present. So, now if I solve this equation, then actually I really do not have to worry about my eta. So, this is called the combined non-linear free surface boundary condition. Now, here you can see there is no presence of eta, right. Okay. Now, let us just little bit do some maths quickly. Here I can see that I just replace that grad phi over here, I replace the grad over here, and then if I multiply by the z. So, I can get here. Now, you can see that only del phi del z term exists, right. So, therefore, I can replace this as g into phi z, right. So, this is basically the the most simplified case for the combined non-linear free surface boundary condition. These are elementary mathematics that you can follow very quickly, like this grad phi is this one, then grad is this, and then I multiplied by the z. So, it is k del phi del z multiplied by the z del z of z. So, therefore, we will end up getting del phi del z, and then we replace the del phi del z over here. Okay. So, maths part is elementary. So, but the important part is here, this boundary condition we do not have eta. So, if I try to solve some problem and try to find out the what is my free surface, what is the velocity potential of the free surface, the water particle. So, then you can use this equation. Okay. So, now this expression, as I said, it is free surface boundary condition, absence of the wave elevation. Dealing with the non-linear free surface boundary condition is very complex, and it is very difficult to solve the real practical problem. So, therefore, we have to make some kind of approximation, some assumptions, and then we need to drop some terms, and we have to get a simplified equation, and then we are ready to solve the equation. So, let us now see that in case of the nonlinear boundary condition, what approximation we make, so that I can find a simplified linearized equation. Okay. Now, this is your nonlinear free surface boundary condition. Now, here you can see we have nonlinear terms such as phi x eta x, this one, and phi y eta y. So, we need to drop this to get some linearized free surface condition. So, what is the approximation? Approximation is we assume phi x and eta x both are very small. Now, if both are very small, then multiplication of the product should be too small, so that we can ignore. So, this is the underlying assumptions. So, under these underlying assumptions, we ignore the contribution for phi x eta x, we ignore the contribution of the phi y eta y. But the question is, at which z actually you are applying it? This is a very important question. Now, ideally speaking, we should apply at z equal to eta. That means, you should apply this equation at the exact free surface. However, in case of under the assumptions of the linearity, we apply at z equal to 0. Okay. And then finally, we end up getting this kinematic free surface boundary condition, what is called the phi z is equal to eta t. Now, let us try to understand what is the meaning of this linearity. Now, here you can see that this is a wave elevation with various z by L, okay, or h by L, that means height divided by the lambda, the length, I mean the length between this from here to here. So, now you can see this is called the, in it's frankly speaking, this is called the wave stiffness. Now, you can see that this h by L, it is 1 by 10 means it is very stiff. So, I decrease the step slowly, see first is 1 upon 10, and after that it is 1 upon 12.5, after that is 1 upon 15, 1 upon 25, and then finally it is 1 upon 50. And then actually you can see when it is 1 upon 15, this elevation is really small. Now, what is happening that this I can think of a linear range. So, what we are logically what we are trying to say as follows, we are trying to say that in case of this small amplitude, we can assume what is happening at z equal to 0, the same thing is happening at z equal to a or z equal to eta. Okay. So, this is the underlying assumptions of the linearity. We have to understand this, right. We assume that when you say it is a linear problem, we assume that what is happening at z equal to 0, the same phenomena is happening at z equal to a, because the elevation is very small. So, that assumptions not hold. These assumptions we cannot make if we take this point, if I take these waves or if I take these waves. We cannot say what is happening here, the same thing happening here, not possible. But however, in case of a linear range, we could say that what is happening here, the same thing is happening here, and that is why we change the range the z equal to eta to z equal to 0, right. So, this is the underlying assumptions of the linearity, and one has to understand very well because otherwise it is very difficult to find out that what is the linear range. When you say it is a linear range, it is a non-linear range. Everything depend on the fact that as long as we can assume what is going to happen at z equal to 0, the same thing is happening at z equal to eta, we really can't progress. Okay. Okay, so, let us stop here, and in the next lecture we are going to discuss about the linearity of the dynamic pressure, and then we have to deal with like how we can solve this problem and how we can obtain the phi. Let us now talk about the linear dynamic free surface boundary condition. Okay. Now, this is the nonlinear equation as you know. Now, here also we are going to apply the same thing. We are going to drop the quadratic term, which is this one, right, half of grad phi square. So, if I drop this term, so therefore, we can get, and also okay, also we have to apply at z equal to 0 in this case also. So, again the logic is similar, what is happening at z equal to 0, same thing is happening at z equal to eta. So, therefore, I can drop z equal to eta and I can write z equal to 0. So, therefore, my linear dynamic free surface condition becomes phi t plus g eta equal to 0 at z equal to 0, right. Now, when I linearized my kinematic free surface condition and dynamic free surface condition, actually I can combine the both. So, my idea again, I need to eliminate either eta or I need to eliminate either phi. So, let us see. Now, this is my linearized kinematic free surface condition phi z equal to eta t, and this is my linearized dynamic free surface condition phi t plus g eta equal to 0, right. So, now I differentiate this equation with respect to t. So, I get phi t t plus g eta t should be equal to 0, right. Now, here I can further replace eta t equal to phi z. So, if I replace this, then finally my equation comes phi t t plus g phi z equals to 0, right. So, this is basically my combined free surface boundary condition, and remember the next one which is in the bottom is basically the combined nonlinear free surface boundary condition. Now, here also if I drop the quadratic term, right. So, and if I apply it is at z equal to 0, again I can get the linearized free surface boundary condition, right. So, I drop this term, I drop this term, and therefore, from here also I get phi t t plus g phi z equal to 0. So, you can see that whatever the approach you are going to take, finally, when you linearize both the things are same. Okay. So, now in the linear problem I am going to deal with this combined free surface boundary condition phi t t plus g phi z equal to 0, and if I want to go with the nonlinear, so then I have to deal with the phi t t plus half grad phi dot grad phi square plus 2 grad phi dot grad phi t plus g phi z equal to 0, this one. Okay. So, now let us see mathematically what are the boundary conditions that we are talking about. So, this is the del square phi equal to 0, that actually it is applied in the whole fluid domain. We have discussed this in last class, and then the initial condition we will discuss again later. And now, this is your nonlinear free surface boundary condition, we apply to the free surface, and then this is the linearized free surface boundary condition which applied at z equal to 0, right. Also, we have the body boundary condition, we discuss this body boundary condition later on. Right now, we are not going to discuss this, and also we have the bottom boundary condition, which is basically the normal velocity, the fluid particle in normal direction is 0. So, fluid does not have any velocity in the direction of the normal. So, this is the bottom boundary condition, right, and also with this we have the radiation condition. So, basically when we are going to solve for phi, we have to apply this del square phi equal to 0 and then all other boundary conditions. So, now let us quickly check like the what is the floating body problem and what is the conditions and what is the the equation that we are going to solve. Now, in case of a non-linear problem, we are going to solve this Laplace equation with non-linear free surface boundary condition, and apart from that the body boundary condition, bottom boundary condition, initial condition, the radiation condition, right. So, this is actually SB is called the exact weighted surface, which is the exactly the free surface, and we call this as a non-linear problem. And in case of a linear problem, everything is same, only the free surface boundary condition is linearized, and also this we are talking about the S0, which is basically the mean weighted surface, remaining thing are same. Just what is this? From this diagram I can see this is basically your S beta or the blue one, and this black line is basically your S0. Okay? Fine. So, now this is basically the boundary value problem that we need to solve to get the solution for the phi. Okay. So, from the next class we are going to get how we can get the solution for phi solving this problem, okay. And today we are going to finish here. Thank you.